So, so let me start with a few words about what we did, and then from today on, we will discuss how to deal with singularities. So certainly this is a very crucial part of the whole proof. So let me say what we did. Actually, it's quite easy to summarize. So then we can. So suppose I have a closed manifold. Okay. So we look at the Ricci flow, and so we start from some metric, say G0. So it's some Riemannian metric. Okay, and suppose such that we normalize this such that the curvature of this is 1. So this can be always achieved by scaling the metrical property. So, and also the volume, say, of a ball, of this unit ball for any point is big equal to some fixed constant. Okay, some fixed constant. So then we run the Ricci flow. So starting from this, and Luis already did. This always exists on a certain. You can always have a solution for certain capital T. So what I did in the last 4 lectures was to prove a few important properties of this. So basically, what I did first, we need to use later. So it's a so-called curvature pinching estimate. So namely, there is always a phi. Okay. A function phi such that say from R to R plus, such that this limit of a phi of say a goes to infinity is 0, and this curvature is bounded from below by these things. So R is a scalar curvature plus C minus C0. So and constant C0. Okay. So this is only true when the dimension is so dimension of M is 3. So we in order to prove this, what we did, we discussed a bit of maximum principle, and before that I told you how to write evolution of a curvature in moving orthonormal frame, and then I show you this. So this is a very important property, and we will see how it's used. And the second thing, which is so-called non-collapsing estimate. That's what I did last time. Okay. So this was done by studying these new length functions. I actually probably should say new energy functions. So which was introduced by Perelman. So we prove this non-collapse. This is says the following. Basically, it says if you look at the region, if you have okay. So basically, there are some kappa positive, and the kappa depends on some of these initial conditions, and depends on also on this capital T here, such that this depends on kappa depends on capital T and omega and the initial condition C. Okay. So this so if a curvature C is bounded by 1 over r square on this parabolic ball of say x of t. So this means is a geodesic ball at the time t, and the radius r cross the t0. Let's say t0 minus r square and the t0. Okay, so where this where the t0 of course is less than t, okay, and we want this r square is less equal to t0, so that okay, so then what we know, the area, the volume of a ball of x t0 of r is bounded from below by kappa r to n. So this is actually true for any dimensions, any dimension. So why so this was proved by using these new energy functionals introduced by Perelman. So last time I said this is with this we can exclude certain types of possible singularities. For example, cigar solution cannot be embedded as cannot be approximation of a Ricci flow of here at any finite time. Okay, so also you can think it's and soon you will see it's because when we try to analyze singularities, we want to take a certain time. We have to take a point where the suppose singularity is forming. So we need to blow up that the region near that point. So then in order to make sure this region exists, you can have a blowing up limit, so that then you can analyze. You not only need a curvature bounded, which can be guaranteed by a scaling, and you also need to make sure volume is good, so that it's not like shrinking to something you cannot see in the limit. Okay, so this is a thing. And the third thing I record here is which I didn't really do. I only in the last time at the beginning I indicate how it can be proved. So this is called a higher order derivative estimate. So high derivative estimates. So this basically says if a curvature is in if a curvature so it's bounded, it's bounded on a ball of this type. Okay. So maybe I stated a little bit more precise. So if if this is bounded on let's say on this let's see x of t0 of t0 and maybe t how do I say? So let's see at t0 of put 0 here, and of r cross 0t, t prime. Okay. So then what you can do is then the derivative of curvature kn, k, will be bounded by some constant. So I actually stated the version which is slightly more general than this one. So depends on ck of t of maximum of k. So it's let's put it this way. So it's k over 2. Okay, k over 2. Okay. So ck prime is some constant. So this will imply say when you if you evolve the metric forward for in a certain positive time, then the derivative will be bounded. Okay. So the key things here is try to bound the curvature here. So basically what though I special for those two, I spent some time to prove that, and the proof as usual was a bit technical. Okay, but this is what you need to bear in mind before we go on. Okay, so you don't really need to know how they proved for a while. Of course, they are. Yeah, it would be nice if you go back to study how it's proved. I think there are certainly very nice arguments. So now the issue becomes so I know there is a capital T. So now I want to see how far I can solve the flow. Okay, how far I can find the solution of this Ricci flow. So I want to find the maximum time so that the Ricci flow exists. Then I want to examine how flow behaves as the time approaches its maximum time. So first let me characterize what the maximum time is. So here is a proposition. Okay. So the proposition says it's basically called long time existence. Though it's basically corollary of this 3 here, long time existence. Okay. So this assumes that if let's take these things over there. So if mgt is a Ricci flow, okay. So let's just state maybe to be nice. Let me restate a little bit. It's a maximum. It's a Ricci flow on a 0t. Then either gt extends across capital T, or then the limit of so the T goes to capital T, okay, and this maximum of a curvature is infinity. So this basically says either the curvature has to blow up, or you can actually extend the flow across it. So the capital T is not maximum time. It's not maximum time. Okay. So let me outline a proof of this, because this is a starting point of analysis for singularities. So the proof is very simple. So suppose this is not so let's say suppose this is not true. So namely the curvature is bounded. So suppose let's say curvature bounded. So suppose the curvature uniformly bounded. So this is say a maximum of so suppose Rn of xt are uniformly bounded by some constant c. Okay. So then that's immediately implies by this high order derivative estimate, that implies the covariant derivative of a curvature tensor are bounded by a t of a k over 2 of c. Okay. So namely, all derivative of a curvature are bounded. So now let me go back to see these things here. So that first thing you can get here, since you have this the metric, this family of metric satisfies this equation here, then immediately I will get this is say the g of t, say g of this xt, okay, at the point is bounded by some so now the ratio here t prime. Okay, so a fixed point and look at the ratio of a matrix at a different time. Of course, this is understood as two matrices. Okay, I guess this is not quite rigorous, but let's put it this way. So then this is bounded by so there's a constant here. So this is n minus 1. So this is dimension-free things. So this is n minus 1 c. Let's see. So exponential n minus 1 c of t minus prime of g x t prime. Okay, and then this is bigger equal to exponential minus n minus 1 of c of t minus t prime, and let's put the absolute value there, g and x t prime. Okay, so then you immediately get this is because this is well, as a t and t prime both sufficiently close to capital T, I mean the difference here is, I mean, this is very close to 1. So you immediately get this is actually for each t is uniform continuous. In x. Okay, xt. So it has a limit. So uniform continuous for in xt. So limit of gx t. I mean, maybe after taking a subsequence, this is exists. I mean, actually, sorry, it don't need to take subsequence because of this. So this exists. So this is at least in the C0 norm. Okay. So now we want to do for CK norm. So in order to want to say this is actually this limit exists for CK norm. How do I see that? I just need to bound all the derivative of this uniformly. Okay. So in order to get a CK norm, I need to bound derivative. Firstly, look at the connections. So maybe I put it this way. So write down since we already did this before. So I can take L K I J dt. The equation. So this is minus G K L of then the Ricci curvature of I L J, and so here is a covariant derivative. So it's J L I minus I J L. Okay. So that immediately implies this is uniformly bounded. So because here are all bounded and this is already bounded, so gamma k I j are yield. So maybe I should say this is not a tensor. So let me fix some connection of G0 of Kij. Okay, so these are uniformly bounded. So after that, you can easily do. Once this is uniformly bounded, what you can do is for example, you back to your flow. You take let say this denote connection, the covariant derivative of G0. So then you can get the G of say d bar of Gij dt is simply equal to minus twice of Ricci d bar. Okay, and this can be written as minus twice of d bar minus d of Ricci and minus. So this, by assumption, this is bounded by assumption, and this is bounded because this is a curvature and this is connection is bounded by here. Okay, the difference is just given by connections that are already bounded, so that then this side are uniform bounded. So this way you can bound the first derivative of G, and you can keep doing this. Okay, so keep doing this, you get the. You keep doing this, you will get so repeat this process. So repeat this process, you will get this K for LG are bounded for L. So once you do that, then you know this actually is a smooth convergence. So this G xt converge to a G in a C infinity sense, x capital T. Okay. Of course, here I take this as a definition because a priori I don't have this metric here yet. So this metric is defined as a limiting of that that solution for the Ricci flow. Okay. So once you have this, now I have a smooth metric, then you can continue. So by local existence, you can extend across. So by local existence theorem for Ricci flow, you can extend. So one can extend. GT. So across. So that's end of proof. Okay. So now we have this simple. We have this result here, proposition here, which tells you exactly when the flow stops. Okay. So now what I know as a say. So this is the time. So suppose I have this. This is my space. Okay. So I evolve your flow at a certain time, capital T. So I have this. Right before that. So maybe I have a part, and then I have this. This part which curvature become very, very big, and so this part might be very complicated. So you also might have things like that, or very. So this is right before the time T. It's hard to draw the picture. Okay. So this is the part, or this is the part where the curvature gets big. So curvature goes up. Okay. And here the curvature goes up. And these regions and the curvature will stay bounded. So those are regions where those are regions which cause us problems, because we cannot at this moment we cannot extend this part across that. Okay. So and this region, since the curvature are bounded and locally the space become very, very curved. Okay, so it become very, very curved, and even topologically, a priori, I don't have a control on that. So what is the next step in order to make to be used to make a flow useful? We have to analyze things here, and analyze. So we need to analyze. So we need to analyze these regions where the curvature is big. So how do we analyze them? How do we analyze them? So one way to do that in a standard maybe analysis or geometry today now is we try to scale them up. So we try to, in order to analyze them, we fix some point here. So we take some point, say, or take some point here, say x depends on t. Okay, so pick up some point. So we pick up some point. So p. So maybe take in this region. So which may depend on t. So maybe I put ti here. Okay, and the ti goes to infinity. Ti goes to capital T. Okay, so such that the curvature is big. So let me put this. I just put I here and Ti. So this curvature is very big. So it's big. Okay. So that's where the singularity is developing. So what we do is we want to analyze the structure of nearby things. So what you do is you scale them up, you blow up the solution. So you set that's a typical way to do that, is set Gi. So maybe set Gix T to be a Qi and the G of your X, and then you put Ti and plus Ti and plus Q T. Okay. So you know this one, if you since you use the equation there, you can easily see using a formula for curvatures. You want to see this also satisfies. Then this also satisfies Ricci flow. Okay, and this one exists on what? So this one is certainly this is well defined on the N. Okay, and cross this. So when the Ti is 0, so this is minus of Qi Ti, and then you can go all the way up to so this is capital T, so Qi and the capital T minus Ti. Okay, so this is so the only things here is bad is you look at this Xi here. Okay, so this is very big, even though this is well defined on the whole manifold. So now you want to take a limit to see what the limit things. So once you take a limit, so like you are standing here, and you look at from as a base reference here, you look at other points, and from this point, but the distance become much bigger because, for example, distance between these 2 points is multiplied by Qi in the new scale, in the new metric. Okay, so in the limit, so you may not see some of these parts. Okay, you might only see these parts near around this point because how much you can see in the limit very much depends on how large this Qi grows. Okay, so but that's fine. So in a sense, so this you do this process, you let I sufficiently big, and hopefully you have a limit, and in the limit you somehow see a limit is a model for singularity, for the structure of this manifold around this point. Okay. So however, I mean this is just a thought. But how do you make it true? You need to answer a few things. So we hope. So we hope this is the limit, maybe up by at least by taking a subsequence. So maybe I put this way. So M and the GI, and then you have a reference point. So I want to say this has a limit. And which which can be understood topologically. Topologically at least, or geometrically at least. Okay. So then you have a couple of issues here. First, so what do you mean have a limit? So we have a few questions here. So is a limit exist? Okay. And how to analyze that? How to classify limit? Okay. And so if we can answer these two things, at least I can understand the nearby this point, the structure of a manifold. Okay, structure of manifold. So I should say why I do this scaling. I know this is a curvature here. So curvature at this point, 0. Okay. So norm of this, if I compute in terms of GI by the scaling property, this is exactly just a QI inverse of a Riemannian curvature of G at xiti. Okay, and this become 1. So I normalized. So that's how I scale. I scale it so that at one base point curvature become 1. So then I need to know whether curvature will stay bounded in the finite distance, because so in order to guarantee this, we need certain compactness theorem, which I'm not going to discuss in details because it's kind of tedious to do it here. So basically, we have this Cheeger and Gromov type compactness theorem, which says if you have a curvature bound, okay, if you have a curvature bound, and if you know it's non-collapsed, namely the geodesic ball has a relatively big volume, then you can take a limit. Okay. So things that we need to do is we not only bound the curvature at a given point, also want to bound the curvature of this metric for any point which has a finite distance from this base point. Okay, in order to guarantee that. So in order to guarantee convergence, because non-collapsing already guaranteed here. So this property is a scaling invariant property. So that's why this is important here. So once I can bound the curvature, which is not trivial at all, which I will state soon, and probably say something later, but not today. And once I have that, I have non-collapsing, then I can take a limit. Okay. So now how do we classify them? So probably today I'm more on this part. So then you say, okay, why? So I want to classify. In general, this is still a very, very difficult question. So, but we can to some extent we can do that in the 3 dimensions. and which is suffices for our purpose. So why we can do 3 dimensions? That's because we have here. In the 3 dimension, we have this curvature pinched property. We can either call them as so-called almost positive curvature or almost non-negative curvature. We can according to a parameter, we call this is like phi C0 almost non-negative curvature. Okay, you can. So this property will be used here is in the following sense, because my Qi goes to infinity. Okay, so once the limit exists, so I basically at any point which is in the finite distance from this base point with respect to this metric, curvature blows up in the original metric. Okay, so once the curvature blows up, because this is guaranteed here, so then I look at here, the negative eigenvalue is compared to the positive eigenvalue is much smaller. So in the limit, by 1, in the limit, so by 1, so that's by 1 the limit has a non-negative, has a curvature in a dimension 3. Okay, it's a dimension 3. So that makes things more, possible. Okay. So now let me go to more detail how we do it. It's there are a lot of quite beautiful results here and new results here, and so now let me make a definition. Okay, before I make definition, maybe I'll expand a little bit. So you think, so one thing I said is this is by 1, the limit has a non-negative curvature in dimension 3. And also you can think since Qi goes to infinity and the Ti certainly bounded from below because the Ti approaches to capital T. So this actually goes to minus infinity. So whenever limit exists, and this limit limit where as a flow, as a solution to flow will exist on a whole time interval for all the way to minus infinity. So that's actually give motivate the following definition. So it's definition of ancient solution. I should say this starting of this kind of ancient type solutions is actually you can do that things for every parabolic type equations, except the only thing is sometimes you cannot do it, sometimes you can do it. This is one case we can do to a large extent. Okay, so this is an ancient Kappa solution. So maybe I put this way. So here is a definition. So first, it's a ancient solution means the following. Is a Ricci flow. MGT. Okay, and you should. This is different GT defined on a minus infinity to 0. Such that first, for each t, M is complete. Complete. Okay. And and the curvature operator with curvature operator non-negative. Okay. And bounded. So this is ancient solution, and I say it's so this ancient is ancient kappa solution, or simply a kappa solution is here. We include this, so is the ancient solution. Which is kappa non-collapsed on all scales. On all scales. Okay. So this is the actual property we part. Okay. So ancient solution already studied for rich flow already studied a lot in previously, and so once Perelman had this actual condition here, so he considers smaller class of that. So I give you a few examples. Just I quickly discuss this. For example, last time I said cigar solution is an ancient solution. But not a kappa solution for any kappa. Positive. Okay. So that's I already checked last time. So there are a couple of other results, and so second, you take say S2 G0 so G0 is a standard Round's field. So then the GT equal to 1 minus T T0, okay, is a kappa solution. So when I say kappa solution, it means the ancient kappa solution, just to save time. Okay. So this you can check easily. Okay. So also it turns out using a result of Richard Hamilton and some this actual consideration here. So this one can actually know the fact. So any two-dimensional, which the proof, complete proof is in the book, but I want to have a time to do it. So let me just state it. Any, say I already assume oriented, otherwise you take a covering. Okay. So any two-dimensional kappa solution is a Round's field. Is this in this example? It's a rescaling of above GT. So basically, up to scaling, that's only ancient solution in 2 dimensions. So in some sense, so I said before, it's an ancient solution supposed to be a model for singularity developments. So So this somehow indicated in 2 dimensions, life is much simpler. You don't have ancient solutions. But even for 3 dimensions, we don't know all the ancient solutions. Okay. So third example is basically I go to 3. So this is say S2 cross R. Okay, and with the GT equal to 1 minus T of G0 plus ds squared is a Kappa solution. Okay, it's Kappa solution with R. So not only this, you can even take the quotient of this. It's still a Kappa solution. So any and so does its quotient. So let's put it this way, where take xs to minus x. Okay. So this is those are basically two ancient solutions which we really used. Okay, I mean I should say there are more 3-dimensional ancient solutions, but those two play the key role here because they are not only ancient solutions. Soon you will see they are actually special ancient solutions. Okay. So on the other hand, it's if you look at S2 cross S1, see this one. Okay, maybe I put it this way: S1 of some radius r. So this is not a Kappa. So this is again it's same as 1 minus T of G0 ds squared. It's the ancient solution. But Kappa collapse, not Kappa non-collapse. Okay, that's because if you have this compact factor here, the volume become bounded. The contribution to a volume from this factor become bounded. So we will not will violate this property here as long as your radius is sufficiently big. Okay. So what is the significance of this ancient solution? So this is it's at least can be shown in the following theorem. This is one of in my opinion is one of the major contributions in this proof. Is theorem, which I certainly I cannot prove it, and if I have maybe early next week, if I may have some time, I do some to indicate how this can be how this can be proved. Okay, so this tells the importance of ancient solutions. So the result is the following. So giving a epsilon positive and kappa positive, and also this condition in the positivity of a curvature. Okay, in that number 1. So there is R0 positive, which of course depends on this constant with the following property. So if GI So the property is following: if a GT is a solution of Ricci flow, on a so on a M3, this is on a 3 manifold on a This theorem is only proved for 3 manifold. Hopefully, one can prove this for all dimensions, but so far the argument do not go through. So let me see, and which is phi C0 almost non-negative. Is of a non-negative curvature. Of course, in 3 dimensions, I have it. If I started from right initial data, I have that things. So, and also is a Kaplan collapsed. On the scales, on the scales less than R0. So then for any x0, t0 with so this is not a big assumption here, because you can, just for convenience, because you can always make sure you choose, you scale the right initial data so that you have a local existence up to a certain time. Okay. The singularity won't develop until time past 1. Okay. So this is just for convenience here. So, and the Q defined to be a ring to x0 of T0. So as the scalar curvature of this is bigger to 2. So the solution, maybe I state first. Solution is in this region, distance of at T0, x0 less than epsilon Q is let me after I explain it a bit later. After scanning Q epsilon close for part of some kappa solution. So let me explain it a bit here. So first, we have to understand, as I said before, have to understand the part where the curvature becomes very big. So this is condition here. So I'm not giving any point where the curvature is sufficiently large. I want to understand the structure of a nearby region. Okay? So this is a nearby region. Okay. So this here, It means this region is modeled on a part of ancient solution. More precisely, this is means the following. So I fix the x0, t0 here. So I look at the GQ, or G bar of, as we did before, of x of t, okay, defined to be this q g of x of t I plus q I inverse t. Okay. I guess q inverse t. Q, sorry. Okay. So inverse, I'm sorry. Okay. So then this region here, so when I say this is after scale, so this distance is actually measured in terms of G bar here, terms G bar. Okay. So in terms of so this region, so let's say this region, this D here, okay. But this is actually in terms of G bar. Okay, I should say in terms of G bar. Okay, or maybe I put the. Okay, so in terms of G bar, and the G bar in terms of okay. Did I say something? Okay, I'm sorry. This is in terms of G. Okay, sorry. This is in terms of G here. And in terms of G bar, this is all the points xt. So this is in terms of G bar now, is the distance of, let's say the G bar here, okay, of a square of x, and x from the base is less than epsilon inverse. Okay, inverse. And the time after this is become minus epsilon inverse less than t less equal to 0. So that's in terms of G bar scale. Okay. So here this is in terms of original scale. So this is the region I'm looking at after scanning. So what the epsilon close means that there is a diffeomorphism. Okay, so there is a diffeomorphism phi to some region in the say time region d0 inside of an ancient solution. Okay, so this is in some ancient solution. Maybe I put this M A and G A T for model. Okay, or maybe A kappa, say kappa. Okay. So such that this is some region here, and you can even let's say this maps to some point here. So x0 goes to some point here, such that this you pull back this. So maybe I put this way back. Okay, it's easier because this is a fixed thing. So such that if you pull back your metric G bar, okay, and compare with this G kappa here. Okay. So this is in the CN norm. Okay, this is actually what we need is like 1 over epsilon plus 1. Okay, this is integral part of that. So in this norm is less than epsilon. This is what we mean. Okay, this is what he means. Okay, so that's the epsilon close means. So you pull back. There are some region basically defined this way, but this is in some kappa solution, and if you there's a diffeomorphism to that. You pull back, then you can compare this solution here. And, okay. So if we classify all the kappa solutions, then we know this region topologically. Then we know this part. Okay. So we know at least a sufficiently large neighborhood of a region where the singularity is forming in a given Ricci flow. Okay. Of course, everything here you have to talk about after scanning. So that's actually one of the subtlety here, because the Q, even if say you can make epsilon very small, so this is a very large region, but in the original scale, because Q could be even larger, so region could be smaller, okay, more smaller. So it is a powerful theorem. But this does not assure you understand all the singularities. Okay. So any questions? Maybe I certainly not going to prove today and tomorrow. So, but I want to state it because I think this gives you some motivations why we need to study ancient solutions. I hope that at least is clear. Okay, so now I want to study give you some study of ancient solutions, because first I pick up this. It's important. I already said that, and second, there are nice ideas here which are presentable. Okay, so how do we analyze all the ancient solutions? So the starting point is the following things. So it turns out there's a special class of ancient solution called shrinking solitons. And in fact, basically all things I stated here are shrinking solitons. Okay, so I mean, except the Cigar solution is only a soliton, but not a shrinking soliton. So okay, so the first statement is the following, which I actually intend to give you some indication how it's proved, but let me first state it at least. Okay. So theorem. Okay. So this in the book is actually 9.11. So let's put this way. So this is actually true for any dimensions, I think. Okay. So let M GT be a kappa solution. Okay, so this is true for any dimensions. Fix any P0. Okay, so this ancient solution is defined from -infinity to 0 in the M cross. So suppose so suppose this sigma k bar is a sequence goes to infinity. Okay. So then maybe before that, let me explain and maybe I state it and then we explain. Okay, so let's how do I do it? So maybe I put it this way. So maybe after taking a subsequence, if necessary. This, I will explain this later. Mk of Gk, okay, T, and the Qk inverse minus 1. Converge to smoothly to a non-flat Ricci flow. So let's put this way. So M infinity. I haven't defined this. I will define this in a moment. G infinity T and Q infinity of minus 1. So where the T is between minus infinity and 0. I cannot guarantee at the, so it has to be open interval. Okay. So such that set non-flat and such that this solution is a Ricci soliton, so it's a Ricci curvature of G infinity at the point T plus Hessian of Gt for some function ft for some function, okay, depends on t, plus 2t of G infinity t 0. Okay. So there's an elliptic equation involved here. So in fact, this equation tells the t is so this thing I'm explaining here. So this is basically says that G infinity t can be written as some family of diffeomorphisms which generated by grading of this f here, star t of G 0 infinity 0. And multiply by some scaling factors. So I will leave you to check this. So in fact, even I write down as a family equation on T, but there's only one equation here. Okay, so all other equations are, all of these metrics are similar to each other. Okay. So that's why I call the soliton type equation, because the form of a metric is, the shape of a metric is not going to change. So they are only up to scaling. They are all the same metric intrinsically. So I didn't tell you what is this. Okay. So let me explain here. So I maybe I define this here. So where. So for each tk, so qk is so qk is defined such that air this from x, okay, from p, okay, and qk you pick out some point and k is less equal to n over 2, which we know is always exists. Okay, and g tau. Okay, so maybe I put a tau here. Tau. You pick up for any tau. You pick up this. Maybe I pick up this. Okay, for any tau less equal to 0, and the g tau of t is simply just given by 1 over tau bar of g tau bar t. So it's a scaling of a metric by a factor Okay, top bias, of course, is positive. So now the GK, so QK is simply a Q sigma K, tau K, and the GK is G tau K. Okay. So that's a convention. So this is basically says following. For example, one of these. So later on, I will have a. So let me first give a consequence of this and draw some. Okay. So one corollary of this. Okay. If say if so let's call this is called G infinity. Call G infinity an asymptotic shrinking soliton. Okay. Of course, there might be more than one of them because it depends on your initial point. Also, may depend on sequences you are taking. Okay. So if one shrinking solid, asymptotic shrinking soliton, let's put it this way, is compact, then this ancient solution is to be Sn. So let me put 3-dimensional case. If n dimension equal to 3, okay, so then this is M3 of quotient by finite group and GT. So why? So that's actually tells you, you see, the ancient solution is, this shrinking soliton is very, how do I say? Okay, so this is used since it's Ivy proved any shrinking soliton. King soliton, soliton in dimension 3 has to be Einstein. So it's of constant curvature. Okay, so that means G infinity has to be like that. Has to be like that. Okay. So from this everything, so I know G infinity, since this is a shrinking soliton, has to be of this form. So now you know your sigma k, your GK after scanning is very, very close to a metric of a positive. So you from how do I say? So let me draw the picture here. So suppose this is our Ricci flow. Okay. So starting from point x. So this goes to minus infinity. So if this is close to a round sphere or up to finite quotient at say sigma k. Okay, and minus sigma k. So then I know since the manifold is close to this, that means your curvature is sufficiently close to a curvature of this, which is of constant. Okay, but then you involve along the Ricci flow, and we know curvature improves, right? Evolves. So curvature is so this is actually the only result of Hamilton, the first. See, in the 3 manifolds, whenever Ricci curvature positive, if you involve the flow, now actually curvature improves this. Okay, so Hamilton 82. See ya. So if G infinity is this, and the curvature pinching of that, so namely the Ricci curvature of GT minus the traceless part of this, minus the scalar curvature GT, maybe I put it this way, divide by 3 of GT. This actually goes down as T, so improves. Okay. So now, since the sigma k is the tau k is very big, so you had some point is very close. So this quantity is very small, because this is very small because it's close to the standard solution. So now you improve this, you evolve this, it become even smaller. Okay, but however, this you can make it as small as possible by taking a sufficiently large k. So that means at any given point, your pinching, curvature pinching, is very small, right? So I say it again. So at any time, given time, you look at the curvature here, pinch, look at this quantity here, okay? And this quantity will be smaller than a corresponding quantity at this point. But this point can be made as small as possible as long as you make k as big as not sufficiently large. So that means this quantity at this point has to be 0. So that is this is 0 for all the time if asymptotic solidity is a standard. Okay. Because asymptotic, in other words, asymptotic solidity is something at minus infinity, and if this become already standard, I mean, if you evolve, you think that as the initial data, it certainly is still standard. Okay. So this tells, so you get it's a standard. So that's very good. Why? Because later on I will show you. In the next step, I don't think I have any time to do some of these proof now. So yeah. So maybe I just say it. So next I want to do is I want to claim another thing, which I maybe to. Actually, proof of this is very nice, and it will give you some actual identity, which is nice. Maybe I say some next time. So next claim is the following. So let me make a theorem. There is no non-compact three-dimensional non-compact three-dimensional shrinking solid. Okay. So why is good? So this corollary takes care of compact ones. So if it's compact, then things are very simple. There's ancient solutions are completely classified. So now we need to move to the cases where the asymptotic solitons are non-compact. Okay. So there are two cases. So one is the curvature. Of course, curvature is always non-negative. So if a curvature is positive, then, I mean, first the curvature cannot be positive because of this theorem here. So you rule out the positivities. So curvature has to be 0 somewhere. But it's a shrinking soliton, it satisfies Ricci flow. So if it has certain vanishing curvature directions, I said before, the maximum principle tells you it has to split. Okay? So that implies asymptotic shrinking soliton are either compact or standard. So then everything's standard, or one of the following, or is S2 cross R. Okay, so this is like a cylinder. Okay, because why is that? Because it's first it's non-flat. It cannot split the two factors because other everything becomes flat. You split only one factor, then you reduce to a two-dimensional soliton. I said before, two-dimensional soliton is just one, right? I mean, actually, two-dimensional ancient solution is unique. Okay, so that's why you only have this. And it might be a finite quotient of that, Z2 quotient of that. Okay. So this is basically what I say here. So you have like a sigma k, qk, and this part, asymptotic soliton here, is always near some like a cylinder, close to some cylinder solution. So this is S2 cross R. So this is near the QK here. And this is gamma, this geodesic. So you also go to maybe QK prime, you also have some shrinking solid. Okay. So that's why probably Luis will discuss this epsilon x. That's how they come out, because they came out as asymptotically part. So maybe I stop here. So next time I will discuss a bit more about ancient solutions here, and then hopefully I can at least topologically classify them.